Hello, happy Christmas and welcome to the final episode of The Naked Scientists of 2012. It's Chris Smith, Dave Ansell and Kat Arney here with you. And to celebrate this festive period, we're going to be taking a look at the lighter side of science this week, including finding out why speed bumps are the best way to diagnose appendicitis, potentially. Also, why reindeer have red noses. The guy we'll speak to has had these animals on treadmills to find out this is a real physiology experiment. And we'll be meeting Cliff, the dog that can sniff for C. diff. Cat.
Boom, boom. We also need you to send in your science questions for us to answer, and we have got a quiz question for you. Can you tell us how much carbon dioxide, that's the fizzy stuff, there is dissolved in a 750 millilitre standard size bottle of champagne? Now, we want an answer in terms of volume, so that's in millilitres.
Thank you, Kat. And we're talking, as I emphasise, normal-sized bottles of champagne, not the mega ones that you drink, Kat.
I wish.
Now, Christmas wouldn't also be Christmas without James Bond, and there's almost always a baddie in James Bond films who gets frozen in something, usually liquid nitrogen, and then smashed into millions of pieces via some route or other. What we want to know is, would this really happen?
Well, I thought it would be great to give it a go, but unfortunately freezing people is a little bit against our health and safety policy. So as it's Christmas, I thought we would see what would happen if we freeze a turkey drumstick in liquid nitrogen and see whether it will smash.
How are you going to smash it?
Hitting it with a hammer.
Now, let's go straight out of the blocks because this one is one about time, ironically. And what time is it for you, Nicole? You're in Australia.
Yes, it's about 2 o'clock in the morning.
Gosh, you're a keen listener.
I am indeed.
So you listen on the podcast to The Naked Scientist. The thing we have to ask, though, is what temperature is it going to be for Christmas in Australia?
About 40 degrees.
40?
That's Celsius.
Gosh.
Yep.
So tell us then, because I've always wondered this, because I've never actually been fortunate enough to spend Christmas in Australia. How do Aussies do Christmas then?
Quite usually we have a big lunch. Some people do a hot lunch. I don't know how in the heat. Traditionally, my family, we do a lot of cold meat and salad. That's pretty much it. We open presents in the morning and, sit around in the pool if we're lucky to have one.
But do you have a Christmas tree?
We do, yes.
With snow?
No, actually.
I just at the irony of spraying snow onto a Christmas tree in 40-degree heat. Now, you've got a question for us. What would you like to ask?
I was talking to one of my work colleagues and we were wondering why time seems to go slow on some days and fast on others, and why our brains cause that, and also is it related at all to when we go through a traumatic event that time seems to slow down? Is that the survival instinct?
Kat.
I've been looking into this a bit. Now, I think in terms of just, a day dragging along or going really fast, I think that's actually to do with what you're doing. So, for example, if you've got lots to distract you, you're keeping very busy, obviously the day's going to seem like it's going really fast. If you maybe don't have enough to distract you, it's going to seem like it's going very slowly. So I think that the kind of the brain thing there is just whether your brain is occupied with something else or clock watching. What's really interesting is you sort of talk about a traumatic event and time slowing down. Now, I've not managed to find out anything particularly about that, but I have managed to find out some really interesting stuff. It's a phenomenon called time dilation. A team at UCL, that's University College London, have been looking at what sportsmen and women sometimes describe about the moment they're about to hit a ball or take a pass. It feels like time slows down and they can get in the right place and make a really great shot. John McEnroe's talked about this. Formula One drivers have talked about this. The researchers think that there's something going on in the brain, in the cortex, processing the visual information more effectively. So maybe you're getting more information and it makes you feel like time is longer. Now, they actually tested this involving volunteers having to react to sort of flashing discs on a screen. And they found that if they asked participants to actually tap the screen, they felt that they had longer to make the action than individuals who weren't doing anything. So if you have to make an action, it feels like you've got more time to do it than if you're just kind of watching. But also, if they made people practice it first so that they knew what they were doing, they were really confident, it felt like time really slowed down. So probably for things like elite sports people, they almost literally do have more time because their brain is processing so much information and they feel like they've really practiced what they're doing. Now, they haven't tested this with elite sports people. They've presumably only tested it with students at UCL who volunteer for psychological experiments. I don't know about research that's been done into trauma, but I would imagine that it's maybe the same thing. Suddenly your brain is going, give me loads of information. I need to make a decision here that could be life or death.
There you go, Nicole.
Excellent. Thank you very, very much.
It's a pleasure. Have you got a Christmas cracker joke for us? Go on. Go on, then.
It's very... What do you get if you sit under a cow?
Oh, I don't know. What do you get if you can sit under a cow?
A pat on the head.
Very good. Here's my chemistry-inspired one. Thank you, Nicole in Perth. We're after rubbishy science-inspired cracker jokes as well. I've got one, Dave and Kat. Here we go. You ready for this one? Both of you? OK. And don't groan too loudly, OK. Why did the chemist put a tooth in a glass of water?
Why did the chemist put a tooth in a glass of water, Chris?
To make a one-molar solution, of course. Ooh. Is that not wonderful? Now, look, we've got a really special person with us this week. Normally we have guests in and we interview them about something specific, and David Braben, who actually works in Cambridge, has popped in to do precisely that, and I'll tell you why later. But he also happens to be a natural scientist originally from Cambridge University, so we thought we'd hijack him and put him on the programme as our guest interviewee / question answerer. Hello, David.
Hello.
So, look, you can do this one. This has been sent in by George Griffiths, and he says, I can't get my head around this. Space is a vacuum, right? So how do astronauts move through it? They're moving through nothing.
Well, the idea, if you try sort of swimming in space, it won't work at all. What you've got to do is use something called reaction mass. So if, for example, you had a tennis ball and you threw it against a wall, that would cause the astronaut to move slightly backwards in the opposite direction to the direction they threw the tennis ball. If they managed to bounce it into something and catch it again, they could do that again and again, and that would move them in the direction away from the, let's say it's a wall on a spaceship they're throwing it against.
So this is Newton's laws, isn't it, effectively?
That's right.
Newton's third law.
Yeah.
Because I think someone asked us once if a person was doing a spacewalk and they were repairing the Hubble telescope or something and they got detached by accident from their space rocket, how could they get back? And someone was saying they would throw their toolkit as hard as they could away in the direction opposite to that in which their space rocket was, and they would hopefully get enough of an oomph to move back towards where they came from.
Yes, and I think, if you were to have an aerosol or something like that, that would work as a sort of rocket. But I think they're all always very careful to be tethered.
One for Dave. Nathan's on the phone. Thank you, David, by the way. Hello, Nathan.
Hello. Thank you for having me on the show. And my question is, if you have two identical blades and you take one and you heat it and you cool the other blade, which one will be sharper?
Oh, that's nasty. Dave, what do you think?
The obvious difference between a hot blade and a cold blade on a really fundamental, if it's an incredibly sharp blade, as sharp as you possibly get, and it's down to kind of atomically sharp, so the point of this blade is kind of one atom wide, then the hotter it is, the more energy there is there, so the more the atoms are going to be vibrating. So a hot blade should be a little bit wider than a cold blade. But there's sort of another definition of sharpness, which is how well it cuts things. And I'm not actually entirely convinced that a cold blade is going to cut quite as well as a hot blade, because a hot blade is going to have more energy, and actually cutting is about breaking chemical bonds right on the end of this blade. So it's possible that having a little bit more vibration in there is a little bit more likely to break those bonds, a little bit more energy to break those bonds. So you might find that a hot blade cuts slightly better than a cold one, despite the fact it's slightly blunter.
Tell you what, a hot knife goes through butter beautifully, Dave. But I guess that's not down to sharpness so much.
Well, it's a similar effect. It's hotter, it has more energy to break those bonds, so it goes through easier.
There you go, Nathan.
Well, thank you very much for answering my question.
Pleasure. So have you got a Christmas joke for us? Please say yes.
Oh, a Christmas joke. I wasn't prepared for that.
OK, well, have a think about it, and I'll come back to you in a couple of minutes when we've had a chat to our next guest, and hopefully you'll have thought of one, OK?
OK, thank you.
Now, a group in Oxford have found a new way to help to diagnose appendicitis, and Helen Ashdown from Oxford University is the lead author of this study. Hello, Helen.
Hello.
So tell us about this study. How did this come about?
People sometimes think that because appendicitis is common, it's easy to diagnose, but that's not actually the case, and it can be quite tricky, particularly in the early stages. And we noticed that a few of the surgeons in the hospital where I was working at the time were asking about pain over speed bumps routinely as part of the assessment to work out if a patient had appendicitis. And we realised that there wasn't very much evidence behind this, and it would be a really easy hypothesis to test. So we set out to do a study to test whether this was true, whether pain over speed bumps was associated with appendicitis.
So literally people coming into the hospital who turned out to have appendicitis or were being considered for it, doctors were asking them, when you go over speed bumps, your tummy hurts more.
Yes, exactly. And if they said that they did have pain over speed bumps, they were much more likely to take them to the operating theatre to remove their appendix.
So you decided to actually test this for real. How did you do it? Because obviously you can't subject people to speed bumps. I presume you didn't do it that way round.
No, we didn't do it that way. What we did was we asked patients who'd been referred to the surgical team to complete a questionnaire shortly after they'd arrived in hospital. And on that questionnaire, it asked them for some details about the journey, so how they'd travelled in, whether they thought they'd been over speed bumps, and if they had, whether they'd had any pain over speed bumps. And then we followed them through their stay in hospital to find out what happened, whether their pain just got better of its own accord, as it sometimes does, or whether they went on to be diagnosed with appendicitis and had their appendix removed, and saw whether there was any relationship.
What did you find?
Well, we found that of the patients who thought they'd been over a speed bump and had appendicitis, 97% said they'd had increased pain.
So their appendix problem was exacerbated by speed bumps?
Exactly. So of those that that went on to have appendicitis, they were much more likely to have had increased pain on going over the bumps.
You don't think it's the other way round and that speed bumps cause appendicitis?
The patients that were on their way to hospital were already in pain, so probably not.
What about the idea then that the hospitals could have two lanes in the entry? They could have a lane that says with speed bumps in it, and if it says have you got more pain, it puts them in the right, and that takes you straight to the operating theatre. Otherwise it puts you in the hospital car park and you pay a fortune for parking and then wait in A&E for 5 years.
I think that's a fantastic idea. Would really help with the diagnosis of appendicitis.
But being slightly more serious, the other way round, in terms of it's very sensitive. In other words, it picks up lots of people who, when they get the extra pain, you can say, yes, we think that there's a high likelihood they have got appendicitis. What about ruling people out?
Yes, so that's exactly what it showed. So the test had what we call a high sensitivity. So that means that it's a very good rule-out test. So that means that if you think you've been over a speed bump but haven't had pain, that makes it very unlikely that you've got appendicitis. But the converse isn't true. If you do have pain over speed bumps, it certainly doesn't mean that you definitely do have appendicitis. And actually in our study there were lots of people who said they'd had worsened pain, who had pain that either just got better of its own accord or who went on to have other diagnoses. And
did you consider different types of speed bump?
We didn't look at that. That was something that we thought if we do a future study we could look at the different types of speed bump and whether there's any relationship there.
Super. That's Helen Ashdown. She is a clinical fellow at Oxford University. And do you have a joke for us?
I do indeed. It's
lighten the tone.
Topical joke. Why are surgical textbooks so short?
Let's ask the team. Dave, Kat, what do you think?
I've no idea.
Why are surgical textbooks so short? David Braben, what do you think?
I can't think.
I think you've got us all foxed. Helen, you better tell us.
It's because they don't have appendices.
OK, you made us laugh, so that's pretty good. OK, thank you very much for joining us. Helen Ashdown from Oxford University. You're listening to The Naked Scientist with Chris Smith, with Kat Arney and with Dave Ansell, and with our special guest who's answering anything that's coming his way, David Braben. You'll hear more from him shortly. If you'd like to get in touch with the programme, email chris@thenakedscientist.com or tweet @nakedscientist. Kat, Charlotte's been in touch by email, chris@nakedscientist.com. She says, how does the body maintain its temperature?
Oh, well, this is a great one. So this is something called homeostasis, because as humans we have to try and keep a constant temperature of about 37 degrees because that's the temperature that all the enzymes in our cells work best at. Now there's a number of ways that we can heat up or cool down. It's all sensed by the brain and controlled by a very special bit in the back of your brain. Now there's three main ways you can control your temperature. So if you get cold, the hairs on your body stand up and that provides a layer of insulation, so that's quite important. Or if you get too hot, the hairs lie flat, so sort of cool down. There's also obviously sweating, Humans do sweat. Obviously, ladies don't. But no, humans do sweat. And that, as that sweat evaporates, that provides cooling for your body, because as water evaporates, sort of heat's lost. This physics, this is Dave's bit. But basically, it cools you down. There's also another way that you can heat up or cool down, which is with your blood vessels. So blood is obviously warm. It's 37 degrees. And if you get cold, your blood vessels will shrink down to try and conserve the heat within you. Also, if you get too hot, they will expand to try and lose heat away from your skin. So, this is why you kind of get pink when you get hot. You get really kind of cold, and your blood vessels shrink when you get cold. Also, you can shiver. That's movement that helps to warm you up if you're really cold. And we also do have within us, we have fat that helps to generate heat. This is a type of fat called brown fat. And these cells are just there to generate heat. And they produce energy, but just kind of to make heat and to keep us warm.
All those different techniques. I think brandy is definitely the best one, though.
Yeah, have some mulled wine at this time of year.
Got a joke here from Susie. She says, "What's green and jumps up and down a frog sandwich?" Interesting. Not sure I'd like to eat one of those. Not many people are having a go at our quiz trivia yet. I think you're a bit foxed by this one. We want to know how much carbon dioxide there is dissolved in a bottle of champagne. If we took all the carbon dioxide out, how much space would it take up? Let's ask David, would you like to hazard a quick guess, just to give people maybe a prod in the right direction? Do you know the answer?
I don't know the answer.
What do you think it might be?
But I would guess it's a lot, because you can reseal a bottle and it repressurizes. So my guess is 10 litres.
Whoa, he's going for big numbers. OK, so Nathan's hanging on the phone. Have you got a joke for us now, Nathan?
Why does Santa have 3 gardens?
Why does he have 3 gardens? I didn't know he did.
So he can ho, ho, ho.
Oh, that's pretty good. OK, for off the cuff, I'm very impressed. Well done, Nathan. Thank you very much. Now, waiting in the wings, we'll be finding out why reindeers' noses are red. We'll actually be talking to the researcher who has done the physiological experiments on reindeer noses and what happens when they exercise. He's coming on shortly. His name is Jan Ints, and he's from Erasmus University in the Netherlands. But talking of cold things, Dave, we opened by saying we wanted to know how hard it would be to do what James Bond does and freeze baddies. So how are you actually going to do this experiment?
Well, simply, essentially repeat the same experiment which obviously James Bond may or may not have done in his film, and essentially cool down some flesh. So we're going to cool down some turkey drumsticks, and then we're going to see how they behave once they're cool.
Cool them how?
I have a bucket of liquid nitrogen, which is sitting at minus 196 degrees centigrade.
Oh, yes. OK.
And I'm just now going to pour some of that into a separate bucket, which doesn't really mind getting chicken all over it.
OK. Or turkey even. So this looks like water, really, except it's water that's boiling at minus 196 degrees. So this is where you've taken the nitrogen out of the air and squeezed it down to a very small volume, take the heat away, and it condenses to make that liquid.
I didn't do it. I went to someone else who had already. Yep. But yes, it's just nitrogen from the air, which is cooled down to minus 196. And it liquefies in the same way that when you cool water vapour, so steam below 100 degrees centigrade, it turns into a liquid. So does nitrogen. OK, shall we pop the flesh in then? So a chicken drumstick is actually quite large. So it's going to take a while to cool down. So
you're just going to put this whole drumstick in the nitrogen?
Chuck a couple of these in.
Whoa. You can tell that they're quite warm relative to the nitrogen because it's all boiling up all over the place.
So yeah, we're getting some really violent boiling, and it normally takes about as much nitrogen boiling off as water you're freezing. So, and it's going to take a while to freeze all the way through. So I think we should come back in a few minutes' time.
We'll leave that fizzing away in the background, and hopefully it'll cool down nicely. Thank you very much, Dave. David Braben, question here for you. This has come in from Troy Cheers by email. And he says, this is very noisy, Dave. He says, my mate proposes that if you're in a car travelling at the speed of light with the headlights on, that you could not see the light from the headlights. I say they're both travelling at the same speed, that the headlights would still be visible in front of the driver. Who is correct, and what equation shows this? That's an easy one for you, David.
Yes, not very easy. According to general relativity, in the frame of reference of the car, the light from the lights would still travel away at the speed of light. But the universe around you, the galaxy around you, might appear distorted. So you get a very weird view. But I think that in summary, as far as I can see, and I would need to think about it properly for a bit longer, the light would shine on the surroundings, but there'd also be all sorts of colour shifting going on because of the relative motions of things, particularly of the reflections. So it would be complicated.
But nonetheless, the road ahead would be illuminated. Would you concur, Dave?
I think, actually, if you're actually talking at the speed of light, then essentially physics breaks, so we have no idea. So if you're getting very, very close to the speed of light, then yes, the universe will look very, very small, and although it would appear to us that the light would take years to go backwards and forwards, it would appear to you to take microseconds because the universe has been shrunk.
Dave, thank you. Quick one here from Les Curiata, who's emailed chris@thenakedscientist.com. He says, firstly, great show. He wants to know where the Earth gets its water from. And the answer, Les, is that when the Earth was first made, there was a little bit of water which condensed onto the Earth's surface from the protoplanetary disk, which is the dust and gas that forms and aggregates around a protostar and slowly accretes into the planets. There was a little bit of water in there, but the vast bulk of the water we've got on Earth actually arrived in the form of comets and also asteroids. And there was a paper published a couple of years ago that looked at this in more detail by studying the water that's on comets using isotopes, and they find that the bulk of Earth's water actually came in the form of asteroids. So we know that some came from comets, lots came on asteroids. Now, Wilf James in Letchworth has got an answer to the Christmas quiz. He's suggesting that the amount of CO2 in a bottle of champagne is about a third of the volume, he says, but 10% by mass. So if you think you have an answer to this, we want to know roughly how much CO2, carbon dioxide, the fizzy stuff, is dissolved inside a bottle of champagne. Now, quick question for Dave. Why does smoke follow people around a campfire, wonders James, also by email, chris@nakedscientist.com.
I think there's two effects here. One of them is psychological, in that you always notice when the smoke is in your face and you don't really notice the times when it's not in your face. So this is one of these kind of distortions of the world, because it's really annoying when the smoke's in your face, so you always notice those, so you see correlations when there aren't any. But you do also get effects whereby if you've got a smooth wind blowing across a campsite, a person sitting there will tend to distort that wind and you might get a vortex, so a kind of swirl of air behind you because the air's having to go up round you, and that could pull some smoke in towards you. So I don't think it happens quite as often as you think it does, but there is a bit of an effect there.
Thank you, Dave. This is The Naked Scientists with Chris Smith, with Dave Ansell and with David Braben and Kat Arney. We're answering all your science questions, and if you have a Christmas-focused question, that would be wonderful, but it doesn't have to be. But if you have a joke, that's wonderful too. If you'd like to get in touch, chris@thenakedscientists.com. Now, why are reindeers' noses red? Well, Jan Ints from Erasmus University in Rotterdam has been putting animals through their paces to try and find out. He's with us now. Hello, Jan.
Hello there.
So do they really have red noses?
Well, they do. Of course they do, as everybody knows, and certainly every child knows. But we thought that it was important to rest children assured that the red nose was due to the physiology of reindeers and not due to some intoxicated substance that he might have taken during the Christmas season.
Oh, I see. So you're saying that the reindeers steal some of what's destined for Santa?
One never knows, and I think this uncertainty would cause a lot of confusion and anxiety among children expecting Santa Claus to be transported in a safe and secure manner.
Yes, it wouldn't be good to be drunk driving, would it?
Absolutely not.
So how did you actually do this experiment? What have you been doing?
Well, the serious part to this story is I'm a physiologist working in an intensive care unit in Erasmus Medical Center, and we are very interested, of course, in how the body adapts to extreme conditions. And so we have a extreme physiology aspect to the pathophysiology which we study. And one of the areas of interest that we have is to know how animals adapt to extreme cold and why things like that doesn't work in the intensive care unit when people are critically ill. So we had developed in the area of this research a hand microscope with which we were able to look at the microcirculation, the smallest capillaries in the body actually, in various organs. And I've learned a lot about how the body reacts to extreme conditions. We had also looked at an ear, nose, and throat setting to various patients and thought that we would also get in touch with Santa to address this important scientific question. And we went to the North Pole, to Tromsø, Norway, in the Department of Arctic Biology. There we met Rudolph, and we did a number of experiments with which we were able to solve the age-old mystery as to the origin of his red nose.
OK, so talk us through what you actually did with Rudolph and his pals to work out this red nose question.
The first thing, of course, we had to do was to verify that his nose was indeed red. Because as a previous commentator on your show said, coldness causes vasoconstriction. So one would expect when he's going across the trade winds and pulling Santa's sleigh under extreme cold conditions or living in the North Pole, a white nose instead of a red nose. So how does this work? Well, the nose in reindeers has got a very special function, much more specialized than what we have. And it is actually used to regulate the temperature of the brain. So one must look at the reindeer nose as a sort of a radiator, actually, and it has a countercurrent exchange. And when he exerts himself, like pulling the sleigh of Santa, for example, his body exerts a lot of energy, and a massive amount of energy, and he has to get rid of this heat. And his brain would otherwise start to boil over, literally. And what he does is he pants through his nose, and he cools the blood in his nose, and this goes to the brain, and this is what we call selective brain cooling, actually.
When the reindeer is breathing in very cold air and is passing blood through the nose tissue very close to that air, the blood will give up some of its heat into the cold air, which will warm the air going into the body, so the lungs get less of a shock. But also that nice cool blood then goes closer to the brain, taking away some of the excess heat from the brain.
Of course, it's part of the brain. The brain circulation actually is in that way regulated very closely at 37 degrees. And his feet are, of course, at about minus 40 degrees. So it really is a very, very effective physiological mechanism. And we proved this, actually. So what we did was we took the reindeers and we put them on a treadmill. And we got them to run. And we observed, looking at with infrared cameras, at the heat dissipation, and we showed that they had red noses. And this is what caused us to write this down and to publish it in the British Medical Journal this Christmas.
Terrific. So reindeer really genuinely do have red noses, it's been proven, but you have to look in the infrared regime to see it.
Well, actually, if you look at them normally, they already have a pink color, as you can see in our publication. So what we did was we tried to find out what the origin of that could be, and we compared them to human nose microcirculation, and we found that the microcirculation inside the nose, that they had about twice as many blood vessels in that nose as do humans. So there was also a real functional anatomical reason for the ability of their noses to turn red.
Jan, stay there, because the next question, Tony in Ipswich has a question which might actually be directly up your street, because it's also about thermal control. The guy who you've just been listening to, incidentally, who has discovered that Rudolph really does have a red nose, is Jan Ince from Erasmus University in Rotterdam. Tony's in Ipswich. Hello, Tony.
Hello. Every time I wear gloves in the winter, my hands get cold. As soon as I take them off, they warm up again. I never wear gloves in the winter, and my hands are hot all the year round. So I'd like to know why.
Jan, any thoughts on what could be going on with Tony's hands?
I have no idea, except to say that you must have a very good circulation, obviously. But what could be happening, actually, is you could be having what we call a reactive hyperemia. So that, normally speaking, they might be feeling cold due to an excessive stimulation of the skin, and that once you take them off, they will, vasodilate, open the blood vessels, and allow more heat to come to your hands. But I think, normally speaking, we do wear gloves to keep our hands warm. So I think you must have a very special circulation. Are you sure you're not a reindeer by any chance?
You're not a reindeer, are you, Tony? You're a reindeer, Tony. Dave, what was your thought?
I guess the one other thing might be, if your gloves were too small, you might be essentially crushing them and stopping the blood getting to your fingers, so there's nothing to keep them warm. So you've got good circulation unless you've got too small gloves on.
Possibly. Thank you, Dave, and also thank you very much to Jan Ince from Rotterdam. You're listening to The Naked Scientists, Chris Smith, Kat Arney, Dave Ansell, and also our guest this week, David Braben. We're answering all of your science questions. Kat, one for you. This is an anonymous one that's come in, and this person says, is it possible to spread cancers by doing biopsies? In other words, when you stick needles into cancers in order to take little samples out, in order to find out what is in the cancer, could you accidentally end up with some of the cancer cells getting into other bits of the body in the course of doing that?
There is a risk of that happening, but it is very small. And it also kind of depends on the type of cancer as well. So some are more likely to do this than others. For example, it's quite rare that a surgeon will try and biopsy a pancreatic cancer because of the chance of this happening. But it's one of these, you've got to balance the risks against the benefits. If the risk is that there's a very, very small chance that doing a biopsy might spread cells, for example, into the bloodstream, against the benefits of knowing actually that you do have cancer and you do need to do something about it, probably the benefits outweigh the risks quite significantly. And also just releasing some cancer cells into the bloodstream doesn't mean that the cancer will spread or even into the surrounding area, because cancer cells, they are kind of still quite fussy, and they do need to find the right places to live and grow. So there is a small risk. It's a very small risk, but there is a risk, yeah.
Kat, thanks very much. In a second, we'll be hearing from David Braben about an interesting project he has launched recently and which is taking shape very nicely. It's all about the game Elite. So if you were an Elite geek from about 25 years ago, this is the thing for you. Before that, though, quick update from Dave. What's happening with the meat in the liquid nitrogen? It stopped frothing.
Well, the meat now has stopped frothing, which means it's obviously not pumping much heat into the liquid nitrogen. So we're ready to go if you want to do it now, or we can do it a bit later.
Let's keep it on ice, so to speak, because Dave's on the phone. Hello, Dave.
Hello, this is Dave from Tip City, Ohio.
What would you like to ask?
Well, in viewing some images, telescope photographs of galaxies, I noticed that a large portion of galaxies is made up of a bright center. And I imagine our galaxy, if viewed from one of those other galaxies, might look similarly. And I was wondering, are there planets within those galaxies that, regardless of their sunrise-sunset cycle, are perpetually in bright daylight?
Certainly the density of stars in the galactic centre is very, very high. It's supposed to be thousands and thousands of stars in a kind of 3 or 4 light-year cube at the centre of our galaxy. And there are a lot more stars outside that. So that puts the stars in at about a spacing of about 1/10 of a light year or so. So they're very tight, close together, but they're still quite a long way apart by the standards of our solar system. But there are an awful lot of them. So I think probably there are planets where it never gets dark, but I don't think it's as bright as full day sunlight. But it's an awful lot brighter than the stars we see where we are in the galaxy.
That's a relief. Thank you, Dave. Lots of jokes coming in now. Neutron walks into a bar and says, "How much for a drink?" Dave or Kat? Well, the barman says the Neutron.
For you, sir, no charge.
Excellent. Got it in one. Merry Christmas, says Tony in Luton. Also, an anonymous text. Why are quantum physicists bad in bed?
Dunno.
Apparently, when they find the position, they can't find momentum, and when they have momentum, they can't find the position. There you go. Now, most people would probably struggle to recall what they got for Christmas about 25 years ago, but there was one present that I will definitely never forget, and that was the computer space trading game that was called Elite. And it was an absolute sensation. It took the industry completely by storm, and it was co-authored by Cambridge entrepreneur David Braben, who has since gone on to release a host of other very successful games with his company Frontier Developments. 30 years later, David is looking to relaunch Elite, and he's actually going to do it in, I think, a very unusual way. David, people have already heard you, where we've basically mercilessly flogged you with other people's science questions. Welcome to The Naked Scientist for the second time. So is it possible to better Elite? I mean, it was Elite. It was brilliant.
It's always possible to better things. If anyone's ever made something, it gets out there and you think, oh, I wish I could change this, I wish I could add this. And especially as the technology then was amazingly inferior to what's around now. I mean, if you compare, Elite was 22K of memory. The entire game code, which is less than most emails today. We squeezed every last drop of juice out of that memory and used some fairly wacky techniques called procedural generation, all sorts of things, to make it really exciting in that small space. And it's something that I've wanted to revisit for a very, very long time.
OK, so what will the return, I suppose you're calling it Elite Dangerous, aren't you?
Yeah.
What's going to be special about this?
Well, it's going to use modern technology, so everything will look gorgeous, but also we're taking it forward. We're adding multiplayer, something that I really wanted to do for a long time, so that you can meet other people in the world, and you can see the world change with time as well. So that you might visit a system and you see, oh, they're building a space station. Next time you visit it, you can, the galaxy changes because we can do it via a central server and gradually update changes to everybody. And you can affect the galaxy. You can do things like loading the stock market. Everyone can get together and say, right, we're all going to sell food today and see what happens to the price. So those sort of things, the sort of social events, I think are really exciting. And it would be great to do that. But sadly, there have been very, very few space games released for quite a long time. And part of the reason for that is that publishers don't like making games where you can't do a very good return on investment prediction. And so because there haven't been any space games, there are unlikely to be space games. It's a ridiculous catch-22. When we first did Elite, all the way back in the early 80s, the publishers didn't want it because it was too different to what was around. They wanted 3 lives. They wanted an extra life at 10,000. They wanted a score. They wanted the total playtime to be 10 minutes because they'd got used to games that were in the arcades. And so it's trying to do that. We're using a system called Kickstarter, where people can essentially pre-buy copies of the game and use that to fund the game development. It's a really new thing, but it's very, very interesting. It's very democratizing, if you like, from the point of view of making creative content. So, and I think that is also a very, very exciting development.
How much would it cost you from concept to a piece of software going on sale? How much would that cost you to actually write a complete game from scratch?
Well, for this, we're looking for £1.25 million. That's partly because we've done a lot of the work behind it already. That sounds like a huge amount of money, but then you divide by the number of people working on it and for the period of time. That's what it comes out as. But having said that, it's great. So if people pre-buy the game, it's no different to buying it later. But you end up bypassing a lot of the issues that we would normally come across when you're publishing games.
I suppose that if it gets funded on, because Kickstarter, where you sort of throw out there the concept, you show people what you have in mind, you're inviting them to buy into the concept, that gives you a really strong steer. There's going to be a lot of support for this. Whereas if you've got no money coming in, you think, well, this isn't going to float, so you wouldn't bother to invest any more in it.
Exactly that. But not only that, all of those people contributing can be along for the ride. They can help influence it in the direction you want to do. It is a very new thing, and I think I imagine this will start to happen in other fields as well. But it's bypassing, it's the direct-to-customer thing. Both ways it works very well. So as someone coming along, they can say, oh, no, I really like this. And if enough people think that, then we can steer it in that direction.
Is there not a danger, and might this not put some publishers and people who run companies like yours off because they think, I'd basically got to show everyone my hand rather than make a big splash with a brand new game. Wow, this is amazing, come and try this. You've basically got to tell everyone what the idea is and tell them about it a long time ahead while you develop it. And so does that take some of the shine off, some of the splash, or is that mitigated by the fact that you get such a strong message from potential investors and buyers and consumers of the game that you know it's going to be a hit?
I think the benefit far outweighs the disadvantage. And also, I think there's a lot of cooperation. There are other people now making space games. There's a guy called Chris Roberts, who I know very well, who's just got funded on Kickstarter, in fact. And I'm part of his Kickstarter campaign. He's part of ours. It's a very friendly community. And it's also, because of the people who are involved in that game, they also want this game to happen. There's a lot of positivity out there. And so for people out there, it'd be great if you want to come and join us.
So tell us, how do people go on Kickstarter? What do they get for their money? And when is the game going to materialise?
Right, so firstly, to find Kickstarter, you go to www.kickstarter.com and you look for Elite Dangerous. What you get for your money, for £20, you will get a copy of the game in March 2014, and you can pledge more to that, and you can get more things, get special things in the game. You can be part of the design forums and all of this sort of thing. It's all very exciting, and the ride has already been very great fun up to now. We've got another I think it's 12 days to go. So
you've raised, you need 1.25 million. You told us that. So how much have you got towards that?
At last time I looked, which was just before this show, it was at 910,000.
So you're not far off. That's a phenomenal amount of money. What happens, though, if you don't make it? Are you going to pay for it yourself and so you make the final donation yourself so you reach that target? Because you won't get that investment from the people who have gone on Kickstarter,
no, indeed,
unless you reach the total, will you?
Absolutely. You have to get the whole lot to get it. But I think the important thing is we want to get this made. We will get it made, one way or another. We want to get it made. If we don't get it on Kickstarter, that would be a real tragedy because it won't happen as quickly. But we will fight. We will look for other solutions. But let's look at the positive. Kickstarter, we're going to make it. Come along and be part of it.
And then Elite Dangerous will become reality. I'm really looking forward to it. Thank you very much for coming to tell us about it, David. Quick question. Chris texted in and he says, great programme, have a Merry Christmas, and says, the treatment of cancers by virus technology, how does that work and where's the main research being done? What scientists are trying to do is to program viruses so that they will go into cancer cells, and in the course of growing in the cancer cell, they do two things. One, they kill the cancer cell directly, but also because you have a cancer cell infected with a virus, the immune system becomes much more interested in attacking the cancer cell than it otherwise would do, and you then make an immune response against those cancer cells so that then the immune system starts attacking other cancer cells, including other cancer cells that are not infected by the virus, and the result is that then you get an effect throughout the body rather than just an anti-cancer effect in just one part of the body. Dave, Bob in Mersey has texted in and said, can you tell me please how flints are formed?
Flints are quite strange objects. They are lumps of silica, so silicon dioxide, normally found in amongst chalk. There's some evidence that they form around some kind of organic matter, so something which might make things a slightly different pH inside the chalk. Water running through the chalk can sometimes dissolve out some of the silica, because some animals, so little tiny diatoms and little tiny algae, have a silica shell, and sometimes that can get dissolved out through most of the chalk and then get redeposited in around this organic matter, and then it sort of just precipitates out and forms these flints.
Thank you very much, and I hope that answers that one for you, Bob. You're listening to The Naked Scientists. Chris Smith, Dave Ansell, David Braben and Kat Arney answering your science questions for you this week. If you'd like to get in touch, email chris@thenakedscientists.com. Now, scientists in the Netherlands have trained a 2-year-old beagle who's called Cliff to sniff out patients who have got C. diff infection. And Professor Ivo Smulders is from the VU University Medical Centre in Amsterdam and he's with us to tell us all about it. Hello.
Hello.
Happy Christmas to you.
Thank you.
So tell us about Cliff then. How did you decide to train a dog to sniff out patients with C. diff?
Well, we knew for a long time that C. diff has a particular smell to it, and we are aware of this, but we can only smell this as humans if you really get your nose almost into the features of the patients, which obviously is not very attractive. And about 2 years ago, a patient had diarrhea, and we're very eager, we're very vigilant for C. diff. And I asked the nurse, could this be C. diff? And she said, well, it doesn't smell like C. diff. So then this was just a brief sort of eureka moment, and I thought if she could smell it, then a dog should be able to smell it much better than she can.
How did you then take that forward to discover whether or not that was true?
Well, I knew for a fact, I think that most people know that dogs and, in fact, most animals can smell much, much better than humans. So the only thing I needed to do was to get in contact with somebody who was training sniffer dogs. That only took me a couple of phone calls, and then we gradually trained the dog first to smell bacterial cultures, which is sort of the pure smell. Then we went on from that to the dog training to smell the particular features. And then the most exciting part, of course, was to see if we could actually smell the patients who were not sitting on the toilet, they were just in their hospital beds, and sort out the ones with C. diff infection from the non-C. diff infected patients.
Now, with C. diff, this is a microorganism which some people carry naturally and it doesn't seem to cause disease in them. In others, it does begin to cause disease. So can the dog discriminate between either people who are going to get C. diff as a problem and those who aren't? And also, there are different types of C. diff, aren't there? Different strains, some of which make lots of the toxin that causes the symptoms, others which don't.
Yes, obviously you've done your homework, yes. This was one of the things we were concerned about, because patients can carry C. diff. And in fact, many dogs carry C. diff in their bowel. What happens if you, for example, have taken antibiotics, the C. diff sort of takes over from the normal gut flora. But it's sort of a gradual difference between a C. diff diseased person and a non-C. diff diseased person. Somehow, apparently, the suppression of the normal gut flora and the relative abundance of C. diff does cause this particular smell that causes the dog to be not only very sensitive to that, but also very specific. So he hardly had any false positive results and hardly any false negative results.
So you wander around the ward with Cliff, and he sits down next to patients in bed who have got C. diff?
Yes, that's correct.
And then what do you do, hoik them out and put them in isolation or something?
Yeah, you need to put them in contact isolation because the C. diff easily spreads across wards and even across parts of the hospital. It's contact isolation, so what you do is you use gloves to whenever you're in contact with the patients, and that's how you can contain the outbreak. And there have been serious outbreaks across Europe, particularly in England, and C. diff still is a major problem across the Atlantic, for example, in the US.
So you can pick up C. diff with the dog identifying people, but have you actually done the next aspect of this, which is to say, now we can prove that our C. diff rates go down if we deploy dogs like Cliff on wards?
No, we haven't. No, what we did was like a case control study. We knew which patient was infected, but Cliff didn't know, and the dog trainer who was guiding Cliff on the leash didn't know. So we were walking behind the trainer and the dog and observed whether he sat down at the right patient, and then obviously we could reward him with a cookie. The only thing that the dog is interested in is obviously the cookie, it's not C. diff itself. We don't have enough C. diff in the Netherlands to actually take it one step forward, which would be to use the dog in a sort of surveillance-like way to see if by letting him wander around wards, whether he could identify patients that we are unaware that have C. diff, and in that way you could actually bring down the rates of C. diff in a hospital.
And if we can do it for C. diff, does this mean we could spot other potential colonisers or superbugs or signs of disease using dogs in this way, so people at risk of MRSA or such like?
Well, MRSA is a particular story because MRSA, the bacteria itself is not particularly strange. It's a Staphylococcus aureus bacteria, but it has antibiotic resistance that is hazardous. I don't think that dogs will be able to identify antibiotic resistant versus non-resistant strains of the same bacteria. I do think, and I know for a fact, that dogs and other animals have been used to trace other infectious diseases like tuberculosis, for example. Rats are particularly good at identifying tuberculosis. And there's a whole history of anecdotal reports of animals, particularly dogs, smelling out different types of cancer.
We'll have to leave it there, but thank you very much for joining us and telling us about that. It's a wonderful piece of work. That's Ivo Smolders from the VU University Medical Centre in Amsterdam, telling us about Cliff, who can sniff out C. diff. You're listening to The Naked Scientist. Chris Smith, Dave Ansell, Kat Arney and David Braben with you on this very festive edition of The Naked Scientist. Now, we opened the show by saying that we were going to see if it would be possible to freeze a body and then smash it to pieces with a hammer, as you see happening to bandies and sometimes goodies in movies at Christmas time. And Dave said, well, he couldn't find anybody that would volunteer, so he did go to the supermarket and has bought some appropriately seasonal meat. We have some turkey and chicken drumsticks and things, and you've put them in liquid nitrogen, minus 196 degrees, for most of the duration of the show. They're now probably pretty cold, Dave.
Yep, if you look at them now, they're just sitting in the liquid, sitting as if they were sitting in a bottle of water, really. They've gone a bit white. I'm not entirely sure. That's probably something happening to the fat on the surface and changing
So basically, these whole lumps of body are now at minus almost 200 degrees C.
Really quite chilly.
Getting them out with some nice sciencey-looking tongs there.
Got some tongs here.
Yep, that's
and
hard.
They're hard, and I can try hitting it.
He's got a very large lump of wood on the floor.
So the little bits of it. So if you've got a very thin piece of chicken, it is quite brittle. So you can knock off the kind of little bits, kind of a couple of millimetres across.
Okay, so let's bung it in the bag, and we won't do this out in the open. We'll put it in the bag, and then what are you going to do? Hit it with a hammer?
So first, try hitting it really quite hard on a piece of wood. Nothing's happening to it at all. I will try a hammer.
Oh gosh.
So
I did see a bit of movement there.
So if I can hit it with my hand on the desk hard, and it will survive that. If I hit it hard with a hammer, it has actually shattered.
Oh, let's see. Is it broken? Oh, fantastic. You've actually got all the bits.
You're now
There's 1,000 bits of chicken in the bag.
Falling over your leg.
Yes, okay. I didn't want that. So it has worked.
So it does work, but it's an awful lot tougher than you'd expect. So if you just fell over, you wouldn't shatter into 1,000 pieces. You might crack a bit, because essentially you've got a composite structure. You've got ice crystals there, and you've also got a load of protein molecules. So you end up something a bit like shell. So it's tough, but it's not going to survive a hammer blow.
One of the things that James Bond sometimes does, though, is to use another goodies and baddies as well, is to use ultrasound. Could that work? Because you used a hammer, but that's not very sciencey and sort of 21st century, is it? So could you do it with sound waves?
So basically, you're going to have to hit it with something really, really violent, and if you get violent enough sound waves,
violent,
you're going to have violent. So you've got to be pretty violent to break this stuff up. But if you had incredibly intense ultrasound, you should be able to smash it up. And I think there was a Swedish firm which was suggesting this is a form of burial. So instead of
environmentally friendly funeral,
people,
so rather than cremate people, you sonicate them with ultrasound, having frozen them first.
Apparently, this uses less energy than cremating them.
Fantastic. I didn't think you'd get that to work. But you really have shattered a body part.
It does shatter,
so it does work.
But you've got to try quite hard.
Thank you very much, Dave. So it does work. Well, talking of hard to answer questions, we'd better finish the show with our question of the week. And in our final question of the week of 2012, Thomas Kammerturns in Berlin has sent us this lovely question to get our teeth into.
Dear Naked Scientists, I wonder why the texture of chewing gum changes if you do heavy physical exercise or drink coffee while chewing. Are there enzymes digesting the gum, or does the pH of the mouth change the material?
So why does chewing gum alter its texture the more you chew?
My name is Terry Cosgrove, and I'm a polymer chemist at Bristol University, and I've been working with Revolumer, a polymer company, on chewing gum. Well, when you first put a piece of chewing gum in your mouth, two things to remember. One, it's cold, and two, it's covered in a sugar coating. And as you start to suck the chewing gum and bite it, then the sugar coating disappears, and the flavours and the sugars which are water-soluble slowly disappear, and that's why chewing gum loses its flavour when you chew it. Now, of course, the temperature has an effect. Gum contains a series of materials known as plasticizers, and these are mainly waxes, and when the gum reaches the mouth temperature, these melt, and they plasticize the rest of the gum, making it soft. So as you chew, you lose the flavour and the gum gets softer. Now there's another thing to consider, and that's how fast you chew. Now if you've been training, or if you've just started to chew a piece of gum, or if you've had caffeine which has made you excited, you're going to chew faster. And because these gums are viscoelastic, that means the faster you chew, the softer they can get. If you continue to chew gum, most people find it does get harder, and this is because some of the ingredients become less effective as time goes on, and also there can be morphological changes inside the gum cud. So these are some of the reasons why when you chew chewing gum, it's hard to begin with, it becomes soft, and sometimes becomes hard again.
Terry Cosgrove. So the warmth from your mouth melts waxy molecules that are called plasticizers that are mixed in with the gum, and they make it much more flexible. But if you continue chewing, or with faster chewing, those plasticizers leach away and they stop working, and so that's why the gum then becomes much stiffer again and harder to chew. Next time, we're going out of the mouth and into the bloodstream.
Hi, Naked Scientists. It's Jodie from Plymouth here. My question is about donating blood. Basically, I know that if someone receives a donated organ, that they have to be on drugs for the rest of their lives so they don't reject the organ. So my question is, why don't we have the same reaction when we receive donated blood? Because I know that you don't even have to be related to the person you receive it from. It could be a complete stranger, as long as it's the right blood group. So, yes, I'm wondering how that works. Thank you.
Well, that's one for you to ponder on until we're back in 2013, because we will be back. We've got an update on the situation on our Facebook page. If you go to facebook.com/TheNakedScientists, you will read that we will be carrying on into 2013. The BBC have had a rethink, so our programme will continue on BBC Radio Cambridgeshire. But there will also be some other changes because we are joining ABC Radio National, RN, in Australia. From the 1st of January, our programme will be going live right across Australia every week, and that will become the Naked Scientist podcast. It will be broadly the same as the programme you currently receive. The BBC programme will also continue in parallel and will be slightly different, but will be accessible on iPlayer. Thank you for all of your support and sticking with us through this year and through this rather turbulent journey. I'm pleased to say we appear to have won. Have a great Christmas and a very happy New Year. And to finish things off, Kat, you have got a joke for us.
Yeah. How does a cell get to work?
There must be a clever answer to this. On a cell cycle?
Yeah! Happy Christmas,
You
Chris.
can work these things out. You can work. I've got one back, actually. My daughter showed me this, and I thought that's actually a cracker joke that is quite funny for the first time in ages. Why aren't cars very good at football? Dave, any thoughts?
None other than the obvious.
They've only got one boot.